Hello and welcome back. In a previous video, we introduced the first three words in the vocabulary of ECT: charge, current, and voltage. By the end of that previous video, we advanced a rather intriguing notion that voltages are electric heights. We better justify that statement. In an electric or electronic circuit, everything happens inside a force field. A force field? Yes, an electric field. The same electric field that you studied in first year physics and in high school. A force field represented with that big letter E. Units newtons per coulomb, sometimes volts per meter. But why do we call that a force field? Because it applies forces. Forces to what? Forces to electric charges inside the field. What kind of forces? These kind of forces. You see, two charges Q1 and Q2 in coulombs separated by distance d in meters in feet experience an electric force F. Remember what law was that? That was Coulomb's law. So much for charges inside electric fields. What about us people? Well, we also exist inside a force field, inside another force field. What field is that? Think. That one. You got it? The gravitational field. We people live inside a gravitational field, a field that applies forces on masses. Two masses, m1 and m2, separated by distance d, experience a force F. We live parallel experiences. We who? Charges inside an electric field on one side, and we people in a gravitational field. Charges experience an electric field like that. We people experience a gravitational field like this one. So what? The point is that you and I, we can extrapolate our daily experience of existing inside a force field and better comprehend what happens to charges inside an electric field, inside an electric circuit, inside an electronic circuit. For instance, the gravitational field is what defines heights for us. So, it's not unreasonable to expect that the electric field must define heights for electric charges in an electric field, in an electric circuit, and in an electronic circuit. How are we going to measure those electric heights? I know, we'll measure them in volts. Yes, Charlie Brown, but that's still in the future. Words like up, down, above, below, higher, lower, they all have meaning to you and to me, because we were born, we grew up, and we continue to exist inside a gravitational field. That's right, we live inside a gravitational field. That field is there when you look out of the window, when you watch television, when you go to church, when you pay your taxes. It is a field that has been pulled around you to trap you to this planet Earth and prevent you from flying off into space and to your doom. Our perception of up and down, above, below, higher or lower than, they all depend on the gravitational field that we live in. Think of it. In Australia, up is the other way. If we were to ask this question about which way is up, people around the globe would point in different directions to answer the same question. Which one is right? All of them are right, because they are all pointing against the direction of a gravitational field pull. That's right. Let me ask you a question. Which one of those two balloons, the red balloon or the blue balloon, which one's higher? The right answer to that question is, I don't know. Show me the gravitational field and I'll tell you which one is higher. If the gravitational field is pulling like this, then definitely the red balloon is the higher one and the blue balloon is the lower one. But if I asked you a second time the same question, which balloon is higher? Your answer is, show me the gravitational field and I'll tell you This is the gravitational field, and you answer correctly that the blue balloon is higher and then the red balloon is lower. The third time is a charm. Which one's higher? Show me the gravitational field, you say? Here it is. This time, none of them is higher. Both of them are at the same height, at the same gravitational height. But what is a height? A height is what defines our relative position inside a gravitational field. So, electric heights define the relative position of charges in an electric field? Yes, Charlie Brown, but we're going to get there. Oh. The higher we are, the more potential energy we have. The height of a body is what measures its potential energy. So, what unit shall we use to measure heights? Meters? Feet? Miles? Kilometers? None of the above. We should consider measuring heights in how many joules every kilogram of a body has inside the gravitational field. That is a true unit for heights. Joules per kilogram. When I hurl an egg into the air, at the apex of its trajectory, that egg has maximum potential energy. As the gravitational field accelerates the egg towards Earth, its potential energy becomes kinetic energy. That kinetic energy turns itself into heat and the mechanical work of breaking the shell when it hits the ground. So, is measuring heights in meters or feet or miles a good idea? Let's see. In Vancouver, a difference of 1 meter in height is a difference in potential energy of approximately 9.81 joules per kilogram. In Lima, 9.78 joules per kilogram. In Nepal, 979. On the top of the Everest, 9.76. On the Moon, 162. On Mars, 371. On Ganymede, 1.43 joules per kilogram. So you see, meter is a good unit to measure distances. Heights, not such a good idea. A much better unit for heights would be joules per kilogram. But that is kind of a long name. Let's abbreviate that to CP. CP? Yes, a new unit for heights. The Copernicus. Copernicus? Copernicus who? This Copernicus. Nicholas Copernicus. Who is he? Better, when was he? He was born in the 15th century and died halfway through the 16th century. He was many things. Was a mathematician, an astronomer, a jurist. He was a Catholic priest. He had a doctorate in law, was a physician, spoke 4 languages, was a classic scholar, translator, artist, governor, diplomat, and economist. He is considered the father of modern scientific thought. However, he does not have a unit to his name until today. Today, we have given him the name for the proper unit for heights, the Copernicus. 1 Copernicus, 1 joule per kilogram. By the way, 1 Copernicus is approximately 9.8 meters at sea level. So if you are 6 feet tall, you write down, I am 18 Copernicuses tall. Or if you are 5'3", then you write you're 16 Copernicus tall. How much cooler is that, eh? Yeah, sure, but what about voltages? We're getting there, Charlie. Electric height. In the same way that we define the gravitational heights inside a gravitational field, in an electric field there is also an up and a down direction. There is an electric height, but we measure those electric heights not in joules per kilogram, not in Copernicuses. No, we don't. We measure them in joules per coulomb. And we gave a name to that unit before. We call that a volt. We measure electric heights in volts. That is correct. Which means that a voltage is a height in an electric field. It is an electric height, which is what we wanted to show. Cool, a voltage is indeed a unit of height. Yes, it is, Charlie. We have seen that now. As engineers, we need to have a feel for what a volt is. We need to interpret what a volt is. Let's have an imaginary terrain inside an electric field with 2 points A and B. A is higher in the electric field B by how many? By 30 volts. That means that A is higher than B by 30 joules per coulomb. What is the meaning of that? The meaning of that is that 1 coulomb in A has 30 joules more potential energy than the same coulomb if it were in B. Which also means if we let that coulomb of electric charge roll downhill from A to B, that coulomb will release 30 joules of energy. Or if we insist on raising that coulomb from B to A, we have to be prepared to spend 30 joules of energy on every coulomb we want to move from B to A. That is the interpretation of the volt unit of electric height. Reference level. We measure heights with respect to a reference, and that reference very often is the level of the sea. For instance, we say the city is 800 meters above the sea level, and this one is 1400 meters, 600 meters above the sea level. So those are the heights of those points, all of them given with respect to the level of the sea. We can even give heights of points under the surface of the sea. We say that this point here has the height of -70 meters and this one here -50 meters. Heights are relative, they are not absolute. They are given with respect to a chosen reference for levels. When we're landing an airplane, the reference level is not the level of the sea. It isn't. It is the surface of the tarmac of the runway where we intend to land the airplane. The point here is that heights are relative to a reference level and that the reference level is chosen, is arbitrary and convenient. In our example, in one case the level of the sea was the reference level for heights, in the other the reference level was the runway surface. What is the height of the reference? All heights are given with respect to the reference. How much higher points are than the reference? What is the height of the reference? According to this definition, the height of the reference is 0. It is a convention. Very often, we are not really interested in heights, but rather in changes of height, in climbs or drops. To define a climb or a drop, we need an origin and a destination. And we define a climb as how much higher the destination HD is than the origin. Climb from O to D is height of the destination minus height of the origin, both of them taken with respect to the same reference level. We measure drops inside the gravitational field as how much higher the origin is than the destination. Height of the origin minus height of the destination. That is a drop from O to D. Let's give a few numerical examples. Consider the drop from B up here to C. How much higher the origin is than the destination. Height of the origin 1400 meters minus height of the destination 600 meters. HB minus HC. The drop is 800 meters. It's a positive number. The drop is positive when the origin is higher than the destination. Another example. The drop from A to D. The drop from this point A to this point D under the sea. Height of the origin 800 minus height of the destination minus 70, that is 800 minus 70, that is 870 meters. That is another positive drop. And this one, this is a drop from A to B, from a lower point to a higher point. The definition applies. Height of the origin 800 minus height of the destination 1400 meters. The drop is negative 600 meters. It's negative, indicating that the origin is higher than the destination. Heights are relative, we've seen that, but drops are not. Once we subtract two heights with respect to the same reference, what we are left with is an absolute value. Let's have a review of what we've seen so far. Inside an electric field, electric charges in coulombs, they exist inside an electric field. For those charges, up and down, higher or lower, above or below, depends on the position of the charge inside the electric field. We measure electric heights in what units? Joules per kilogram? No. We measure those electric heights in joules per coulomb. We gave it a name, volts. So we measure heights in volts V with respect to a reference level, which is arbitrary. And then we measure the drop between 2 points in an electric field, also in volts. We say the drop from A to B is the height of A, the origin, minus the height of B, the destination. The voltage drop from A to B is voltage of A minus voltage of B, both measured with respect to the same reference level. Voltage is indeed the electric height. Now the question, where do we put the reference? Electric power grids, they are connected to the planet. So in those circuits it makes sense to use ground as the reference. But in handheld electronic devices, what ground? They are not connected to ground. They are not. If you think that because your hand is touching it and your feet are on the ground, the circuit is grounded, no, you're wrong. All your hand is touching is the case of that device, and the electronics inside are carefully insulated from the case. In those electronic circuits, the reference is chosen arbitrarily and conveniently. The reference is not tied to either the positive or the negative terminal of any battery in the circuit, which is a common mistake to believe it is. It is not. You can choose any point in the circuit as your reference. That is your 0 volts point. Even the negative or the positive terminal of a battery, any battery, but not necessarily. Now a numerical exercise. Heights reference. In this circuit, all heights, that is all voltages, are given with respect to the reference. This point is 5 volts higher than the reference, 8 volts higher than the reference, 11 volts higher than the reference, etc. This point here is 0 volts higher than the reference, so that has to be the reference indeed. Before we proceed, let's identify all the points in the circuit as A, B, C, D, E, F. Which one is higher, B or C? B is 5 volts above the reference and C is 8 volts above the reference. So you tell me C is higher than B by 3 volts. And the same you can do with all the others. You can choose different references. You can say, no, I do not want A to be my reference. I want B to be my new reference. Sure, we can make this my new 0 volts. And then automatically I remember that C is 3 volts above the reference, so the voltage of C now is 3 volts. And A is negative 5 volts above the new reference, so the new voltage of A is negative 5 volts, etc. and etc. Those are the new voltages of the circuit when we choose B as the reference for voltages. You can choose any point in the circuit as your reference. It is coincidental that I chose first A, the negative terminal of this battery here, and in my second example B, the negative of this other battery in my circuit. Oh, that is a coincidence. Let's do that differently. Let's choose in this exercise E as my new reference. So the voltage of E by definition is going to be 0 volts. But B is 2 volts below E, so the new voltage of B is going to be negative 2 volts. What about F? The voltage in F was 11 when the voltage in E was 7. They were given with respect to A. So F is higher than E by 4 volts. So we say this is 4 volts above the new reference. And D is 5 volts above the new reference. And C is 1 volt above the new reference. And what about A? Well, A is negative 7 volts above the new reference. So you see, you can definitely choose any point in your circuit as a reference for voltages. How do we measure voltages in a laboratory? With this kind of instrument, it is called a voltmeter. A voltmeter has two terminals, a black one and a red one. We proceed like this. The first thing is you choose a reference in your circuit and you connect the black terminal to that reference that you chose, and then you connect the red terminal to the particular point X at which you are going to measure the voltage with respect to the reference. The readout tells you how much higher X is above the reference. We do not cut the circuit to measure voltages the way we did for currents. And that is the end of this lecture on voltages, the electric heights. Thank you very much.